stop Trump, it's how we stop the next one. So Donald Trump, since I know you're watching, I have 4 words for you. Turn the volume up. New York will remain a city of immigrants, a city built by immigrants, powered by immigrants. And as of tonight, led by an immigrant.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
Today, I want to do 2 things. One is to discuss geodesics a little more and to explain a little more thoroughly the connection between gravitational forces and geodesics, or the motion of geodesics through space-time. So for the first part of the lecture tonight, we're going to be thinking about space-time, not just space, but space-time. But the mathematics for space-time is very similar to the mathematics for ordinary space. There's also a metric. When we're talking about space and time, instead of using m and n for indices, we use Greek indices, mu and nu. And again, there's a notion of distance, which is called proper time. I'll also write it, well, I guess I usually write it, I have trouble keeping my notations entirely consistent. I'll try to keep them consistent as I can. Instead of calling it ds squared, s is usually the label for distance in space. One calls it d tau squared because it's more like time. Proper time, the proper time along a trajectory has a little interval along the trajectory. It has a set of differential displacements, which are called dx mu. Remember, mu runs from 0, 1, 2, and 3. 1, 2, and 3 represent space. 0 represents time. And the square of the proper time along a little interval like that is defined again in terms of a metric. In general, this metric in special relativity, this metric is constant. Everywhere is the same, and it's usually taken to be the symbol eta mu nu. Eta mu nu is the analog for space-time of the Kronecker delta symbol delta mu nu, delta mn, for ordinary space. And it's given not by 1, 1, 1, 1. It's a 4 by 4 matrix, but it's given by 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. All right, so in other words, it's of the form dt squared minus, if we wanted to replace these by t, x, y, and z, then in special relativity, the metric here would just be d tau squared, or the proper time would just be d tau squared, which is equal to dt squared minus dx squared minus dy squared minus dz squared. That would be the rule in units in which the speed of light is equal to 1. Where would I put the speed of light if I wanted to include it in this formula? Well, if I wanted tau, which is called proper time, to have units of time, not of space, but of time, then I wouldn't want to put the speed of light in front of dt squared, because the speed of light has units. What is those units? Units is units of velocity, kilometers per second. But the place that it would go would be in here, over c squared. Plus like that. All right, so notice first of all that if the speed of light is large, which it is in ordinary units, where the speed of light is large, now what does it mean to say the speed of light is large? The speed of light is the speed of light. It's neither large nor small. It is what it is. What it really means is that the things that we're interested in are moving very slowly with respect to the speed of light, so that we can think of the speed of light as much faster than anything we might be interested in. Under those circumstances, if this object here is moving slowly, then we can treat the speed of light as being very large, and this piece here is essentially negligible. And d tau is the same as dt. So for slowly moving objects in a frame of reference in which everything is moving slowly, then time and proper time are very close to being the same thing. But more generally, if we're interested in things which are moving fast, then this is the proper time along a trajectory. It's the time as recorded by a clock moving with the object. A standard clock made in the standard clock factory moving with the object will record proper time, not coordinate time. This would be called coordinate time. This would be called proper time. Now, in general theory of relativity is related to special relativity in the same way that flat space is related to curved space. We haven't discussed yet what curvature means. We're going to do that tonight. But, yeah.
I have a question. Isn't dt the one that the clock would record if it's moving with the object?
No, d tau is the one that the clock records. The clock moves and ticks off proper time in the same way that if you have a curve in space and you lay out a tape measure along it, the tape measure doesn't record y or x, it records distance along the curve. All right? Think of the clock moving with the object as a kind of space-time tape measure, keeping track of proper time along the trajectory. Each tick of the clock can be thought of as a marker along this fictitious tape measure, the space-time tape measure. The only peculiar thing is that there's a minus sign in here. All right, so that we need to keep track of. But as I said, general relativity is related to special relativity in exactly the same way, or exactly in an analogous way to the way that flat space would be like special relativity, and curved space would be like general relativity, except it's curved space-time. Other than that, the rules are basically the same for geometry, the existence of a metric, the notion of covariant derivative, exactly the same. The Christoffel symbols are made up out of the metric tensor. The metric tensor is a tensor. There are covariant, contravariant tensors, covariant derivatives, Christoffel symbols, and they're all made exactly the same way as they would be in space, except that you use the space-time metric rather than the space metric by itself. Notice there's one time direction with a plus sign, and all the others have a minus sign. Okay. No, this is last week's.
Quick question.
Yeah.
The matrix size, whether it's 4 or 5 or 6, is this what accounts for the extra dimensions in string theory?
Yes. Yes. The number of x's and the size of the matrix is related, not just related to, is exactly as you say, the number of dimensions. It doesn't have to be string theory. Whatever space-time we're talking about, the dimensionality is just the number of entries here, and it's also the size of the matrices. But, you know, apart from that, the rules are basically the same in every dimension, and whether it's space-time or just plain space. All right, now, excuse me. When we're dealing with flat space or space-time, we don't ever really need to introduce curvilinear coordinates. We may or may not want to. In fact, it almost seems like a stupid thing to do because it's going to complicate the description of things. When do we do it and why do we do it? We do it because we're sometimes interested in accelerated frames of reference. An accelerated frame of reference is basically one in which the coordinates of space are being accelerated. Let's say they start coming in from the left and run off to the right, you know what I mean. And the mathematical description of an accelerated frame of reference in terms of an original unaccelerated, what's an unaccelerated frame of reference called? An inertial frame. Yeah, the description of an accelerated frame in Newtonian mechanics, forget relativity for a minute, in Newtonian mechanics, is just a frame of reference. Well, let's see, if we have our inertial frame of reference, Tx, that's our inertial frame of reference. In this frame of reference, all objects move along straight lines. Then the accelerated frame of reference is one whose coordinates are curved, like this. They form hyperboloids. And in this frame of reference, an object which is moving along a straight line in xt coordinates would in fact not be moving along a linear trajectory in the new coordinates, and so it appears to be accelerated. Of course, the object is simply accelerated with the equal and opposite acceleration to the way the coordinate frame is being accelerated. It's just the old elevator story. And had it not been for Einstein thinking about elevators and acceleration and its relationship to gravity, nobody would have been stupid enough to introduce curved coordinates into physics. Why would you do such a foolish thing? It makes things more complicated. And of course, the answer was the equivalence principle. The curved coordinates are the same as a gravitational field. Now, so we do introduce curved coordinates. That itself is not the same as space-time curvature. We'll come to it. But once we introduce curved coordinates and so forth, the whole apparatus of tensor analysis, transformations of things from one frame of reference to another, all of that gets inherited from the geometry of space that we've discussed up till now. All right, let's see. I'm not sure what order to go in. I think we'll begin with curvature. Or should we begin with geodesics? We'll take a vote. Who wants geodesics? Who wants curvature? All right, we hear curvature. Okay. So I'm not even sure why I talked about this. All right. We'll come back to it. We'll come back to it. Oh, yeah, I do remember. Yeah. Curved coordinates are sort of a luxury that you can use or not use in special relativity. But they're not a luxury when you come to think about gravity, in the general theory of relativity, but in particular, even in Newtonian gravity, it's not possible to remove a real gravitational field by changing coordinates. One of these fake gravitational fields, which is just due to accelerated coordinates, that can be removed by just replacing the accelerated coordinates by non-accelerated coordinates. But a real gravitational field you cannot remove that way. For example, if you have a star and there's a gravitational field pulling you toward the star, then in a small elevator over here, you might be able to remove the effects of the gravitational field by just letting the small elevator freely fall, and then all experiments inside the falling elevator would be exactly as if there was no gravitational field. And that's not quite true. It's not quite true because of tidal forces. Because across the elevator, the gravitational field varies a little bit. There's a little bit of tidal forces. But if you make the elevator small enough so that the gravitational field doesn't vary very much, then you completely remove the effects of gravity inside that elevator by just letting the elevator fall. Well, that's like kind of introducing a coordinate frame inside the elevator, which is like the straight line, which is like the inertial frame. And the coordinates which are not falling, those are like the curved coordinates. You can't, however, get rid of the curved coordinates or the gravitational field everywhere simultaneously. There's an obstruction. If you introduce an acceleration vertically, that's not going to get rid of the gravitational field over here or over here. If you introduce a coordinate system which is accelerating vertically, let's say in the down direction, that's only going to make things worse over here. It might remove the gravitational field in the falling accelerator on this side, falling elevator on this side, but the same coordinate transformation will only increase the gravitational field down here. So there's an obstruction to removing the effects of gravity, or an obstruction to finding coordinates which sort of straighten out all the effects of gravity and get rid of them. That obstruction, mathematically, is the same obstruction as the obstruction of taking a general space or general space-time and thinking of it as flat. First of all, what does it mean for a space or a space-time to be flat? In the case of a space, it means that you can find coordinates. It doesn't mean that every coordinate system has this property. It means you can find coordinates which have the property that the metric tensor is just delta mn. More specifically, it really doesn't need to be delta mn. The metric is constant in space. Incidentally, there are coordinates in which the metric is constant in space, but in which it's not delta mn. If you choose coordinates which are at angles like that on this blackboard, but which are completely uniform, made up out of straight lines, equally spaced, then the metric is not delta mn, it's some other numerical tensor like this, but it's constant from point to point. So another way of saying it is that a flat space-time is one in which the metric can be chosen to be absolutely constant everywhere. Okay? To put it slightly differently, the metric can be chosen so that the derivative of the metric with respect to coordinates, notice this is a thing with three indices, the general derivative of the metric with respect to position can be chosen to be equal to 0, you can find a metric, you can find a coordinate transformation which will make the derivatives of the metric all equal to 0. That is a flat spacetime by definition. All right, now, I assert, not only will I assert, I will give you an argument that you can always, at a particular point, here's some curved space, a general space, without even knowing what curvature means, I will tell you right now that it is always possible at a particular specific point to choose coordinates so that at any specific point, the derivatives of the metric equal 0. It's always possible to do. Let's see how we can argue that there's, in other words, there's enough freedom in the choice of coordinates so that at one point you can choose g to have derivatives equal to 0 in every direction. First derivative, the first derivative, not the second derivative and the third derivative and the fourth derivative, but that the first derivative of g can be chosen to be 0 at a point. Let's figure out how many equations and how many unknowns there are. Supposing we have some coordinates, let's call them x coordinates, in which the metric is not constant or does have derivatives at this point. In other words, where the g's are not without derivative at this point. And let's make a coordinate transformation to a new set of coordinates. I'm going to call them y. I'm going to choose the origin of the y coordinates to be exactly the same as the origin of the x coordinates. All right. For example, a simple example would be ym equals xm. That's a dumb coordinate transformation. It's no coordinate transformation at all. But now I want to make it more general than that. And I'm going to assume that we can Taylor series expand, that we can expand y's in x, that we can start with ym equals xm plus a deviation which is going to be quadratic. And then, of course, there can be cubic terms, higher terms than that. But let's add in some quadratic terms. And the quadratic terms will be quadratic in x. The left-hand side has an index m associated with it. So we better put here some coefficients. These are numerical coefficients, just numbers. At the moment, they're not even functions because we're just interested in one particular point. At one particular point, we'll add in, and I'm going to put a CM, RS, XR, XS. This is the most general thing that I can write down, which is quadratic in the x's, and of course, has an index m from here, and XR, an R and S that combine with the x's here. That's, in fact, the most general coordinate transformation, which is quadratic in the x's, and which has the property that the origin of coordinates, namely y equals 0, is the same as x equals 0. All right, x equals 0 and y equals 0 are the same. All right, so all that means is I've just introduced other coordinates located with the same origin over here, but they're curved relative to the x's. That they're curved has to do with this term here, relative to the x's. Okay, how many variables do I have to play with in making such transformations? Let's figure out how many such variables are there.
Well, one question. It looks as if you're saying that's like a Taylor expansion, it looks like you've almost assumed. Did you drop out the first derivative, or I guess you did?
Oh, that's actually here.
Okay.
And I could have made it a little more general than this, but I just decided that the leading term would be y is equal to x. All right, the leading term y equal to, I could have made it more complicated so that the linear term here was a little more complicated, but there's no need to do so. All right, so how many constants C are there? Just for fun, let's see how many there are. C, let's forget the M for a minute and just think of CRS for fixed M. C is a matrix. Just putting our hand over M here, C is a matrix. And furthermore, it can be taken to be a symmetric matrix. There can be a symmetric matrix because there's no difference between XR times XS and XS times XR. So C is symmetric with respect to interchange of R and S, or can be chosen to be so. If we have a space with a certain number of dimensions, let's say D dimensions, then how many independent entries are there for a symmetric matrix? No, D dimensions. Six is right in 3 dimensions.
D times D minus 1 over 2?
D times D plus 1 over 2. Yeah. Remember, we got to get 6. 6 for 3, so 3 times 4 is 12, divided by 2 is 6. So it's D times D plus 1 over 2. We're not going to use this. I just wanted to do a little bit of combinatorics. But now, this one matrix like that, for each entry M, how many possibilities does M take on? D. So the answer is D squared times D plus 1 constant C that I can play with. I haven't chosen them yet. We're going to think of them as unknowns in a minute, unknowns subject to a condition. Now, when I construct the metric in terms of y, how do we do that? We transform from y to x. We transform from y to x, and we'll get a metric starting with gmn of x. We will get a new metric, which we can now call g, well, let's just continue to call it mn of y. It's not the, it's the new metric in y coordinates. Okay? I'm going to require of the constants c the condition in other words, I'm going to try to choose the c coefficients here so that the derivative of g with respect to y is equal to 0. How many unknowns are there and how many equations are there? When I write this out, this will just become an equation. Given what gmn of x is, I'll transform it. I'm not going to go through the whole business. We're going to transform g, find g of y. That's going to involve the constant c, because they'll enter into the coordinate transformation. And then I'll write down the equations that the derivative of g with respect to any given direction is 0. Those become equations for c. How many equations are there? How many such equations are there? Well, there's a symmetric matrix that's d times d plus 1 over 2. But how many such symmetric matrices are there? In other words, there's exactly the same number of components of this object, gmn with an index s, as there are of this object. A thing with 3 indices with 2 of them symmetric. Same thing here, 3 indices with 2 of them symmetric. These equations, there are just exactly the same number of these equations as there are coefficients c. The conclusion is there's just exactly enough equations so that you can always find a coordinate transformation which sets the first derivatives of g equal to 0. So that's something you can always do. Once you've done the first derivatives, if you start looking at the higher derivatives, there are just too many of them. If I wanted to write down higher derivatives here, there are too many higher derivatives to allow you to solve the equations. So at most, you can set the first derivatives of g equal to 0. All right, supposing we've done that. Supposing we've done that and we found coordinates where this is equal to 0. All right, there are various things we can say. First of all, the derivative of gmn with respect to x is equal to 0 at that point. But we can say a little bit more. We can also say that the Christoffel symbols at that point are equal to 0. Why? Because the Christoffel symbols, what are those? Let me write them down for you again. 1/2 GRS derivative of G Sm with respect to xn plus derivative of G Sn with respect to xm minus the last one, derivative of Gmn with respect to xs. This is the Christoffel symbols. And of course, if I have chosen the first derivatives of the metric, if I've chosen coordinates which get rid of the first derivatives at the point, at the origin, for example, then at that point, the Christoffel symbols are also 0. They're made up out of these derivatives. So at the point in question, the single point in question, the origin, for example, doesn't have to be the origin of coordinates, but at the specific point in question, I have succeeded in simultaneously finding coordinates in which the derivative of g is equal to 0 and in which the Christoffel symbols are equal to 0. From that, it follows that the covariant derivative of g is equal to 0, because the covariant derivative of g is just the derivative of g with respect to x plus Christoffel symbol times g plus another Christoffel symbol times g, one for each index of g. I won't bother writing the details. So once we have found coordinates in which this is true and in which this is also equal to 0, we know that at that point, the covariant derivative of g is equal to 0. But on the other hand, the covariant derivative of g is a tensor. The ordinary derivative of g is not a tensor. The Christoffel symbols are not tensors. But the covariant derivative of g, that was the whole purpose of inventing covariant derivatives, to make things which really are tensors. So the covariant derivative of g is equal to 0. It's a tensor, and if a tensor is equal to 0 in one coordinate system, then it's equal to 0 in every coordinate system. Well, there was nothing special about the origin of coordinates. I could have done exactly the same thing at every point. And so I conclude that the covariant derivative of g is 0, everywheres. Just because I can choose coordinates at any point where the derivative of g and the Christoffel symbols are equal to 0. So that's the theorem that...
How do we know that the c's will, when we make them be non-constant from point to point?
We begin by doing this at a point.
Right, but now we are able to extend that to, say, through a curve or something.
Well, you can't know. You got to go. If you go to a new point, there'll be new c's.
Right,
if you go to another point,
the functions going. Those won't necessarily be continuous, would they?
They'll be continuous. Yeah.
Well,
the function c will be continuous, but they will vary from point to point.
The argument's a little circular. You use that the covariant derivative of g being 0 to derive the formula.
That's true. That's true. The argument is a little bit circular. But what it proves is the consistency of the definitions, if you like. You could introduce other kinds of geometric structures where the Christoffel symbols are replaced by other objects. There are other definitions of the Christoffel symbols where the covariant derivative of g, for example, is not equal to 0. Such things are possible. I guess what we really prove here is the consistency of the idea that the covariant derivative of g is equal to 0. We assume the covariant derivative of g is equal to 0. We calculate from that the definition of the Christoffel symbols, and then we go back and we discover with that definition the covariant derivative of g is equal to 0. So actually you're right, the definition is circular. Not completely circular, but yeah. Yeah. In any case, the definitions are consistent, and they are the standard definitions of how you covariantly differentiate tensors to get tensors.
Question.
Yeah.
If this is related to an intuitive notion of flatness,
Yeah.
what would happen if somehow or another, like you had a wiggle, and then inside of every wiggle you put another wiggle inside of every wiggle? So is there a constraint on G such that you can't get a situation that is sort of infinitely wiggly, so you could never find a coordinate system that would be flat?
Yeah. You're asking, for example, whether g could be such an unpleasant function that its derivatives don't exist or aren't continuous or something like that. So yes. So the usual assumption is that the g's are continuous and differentiable everywhere.
Just once, or?
Let's say just once. And there will be exceptions. For example, exceptions are places where the geometries become singular. There will be exceptions, but in general, a place where the geometry becomes singular, I'll tell you what singularity means in a second. I've given you examples of polar coordinate singularities, which are funny right at the origin. All right? Polar coordinate singularities are not well, sorry, polar coordinates are singular at the origin. That's because at the origin you can't give a well-defined angular coordinate to a point. It can happen that you choose coordinates that are defined in a way that make g's not be properly differentiable or something. But on the other hand, you can also find other coordinates at exactly the same point which are not singular at that point. So polar coordinates are kind of bad coordinates right at the origin. But there's nothing wrong or funny about the space at the origin there. It's not singular. And the way to prove it is just to go to other coordinates where the metric is nice and continuous and differentiable. There may be places, honest places, where there's nothing you can do to make the metric differentiable and friendly function at a point. And if that's the case, then one says there's a singularity, a real physical singularity. A real physical singularity is a place where there's nothing you can do, not only not to make the coordinates flat, but also to make them smooth, to make the metric continuous and differentiable at that point. I'll give you an example. We're about to come to an example now. The cone, the tip of the cone is a real singularity in space where there is no coordinate system that you can choose which will make the metric at the tip of the cone smooth. There's something real going on there, and that's called a singularity.
I have a quick clarification on the last term in the denominator of the Christoffel symbol. Should that be x?
Yeah, sorry. Yeah. Yes.
Is this, when you solve for the C, the constant, is that like trying to find a coordinate system where the Christoffel symbol is vanished?
Yeah. Yeah. Yeah, but you can do that by making sure the derivatives of the metric vanish. Right. This, incidentally, among other things, proves that the Christoffel symbols can't be tensors. Because by a coordinate transformation, you can make Christoffel symbols which are not equal to 0 at a particular point. So the Christoffel symbol is not a tensor. The derivative of a tensor is not a tensor. but combining together derivatives of tensors with Christoffel symbols gives you tensors. All right, so good. Yeah, so with this definition of the Christoffel symbols, it follows that the covariant derivative of the metric is 0. And whether it's a good thing or a bad thing, it's a true thing. Now, let's come to the idea of curvature. As I said, curvature is a mathematical obstruction. Its presence prevents you from finding coordinates in which the space is flat. And to understand curvature, you first have to understand something we've already spent some time with, the idea of covariant derivative of a vector along a curve. Let's go back. We talked about this previously, but let me go back to it. That's the starting point. The notion of the covariant derivative along a curve. The question, I'll tell you what question we want to answer. We want to answer a question like this. Supposing I start with a vector somewheres in space, and I would like to move it to another point, keeping it parallel to itself. In other words, I would like to move this vector over to here. And I would like to know what its components are over here if it's moved in a way which keeps it parallel to itself. That's the notion of parallel transport of a vector. Keeping it parallel to itself as you move it, we'd like to move it over here. Now, in flat space, it's pretty clear what you do. You just keep the vector parallel to itself. But when we are we can just choose Cartesian coordinates where the metric is just delta mn. And in those coordinates, keeping the vector parallel to itself just means keeping its coordinates constant, keeping its components constant. But if either we have curved coordinates or a really curved space where we can't choose the metric like this, then we have to find some definition of what it means to move a vector parallel to itself. It's not clear that we can find such a definition, but I will tell you what it is, what an appropriate definition is. All right, first of all, take your curve, take your vector, and make the covariant derivative along the curve. I'll remind you what that is. If we have a vector, let's say it's a vector with contravariant indices, then, and it's defined all along the curve. All along the curve it's defined. It might even be defined in the rest of space, but I'm not interested in it in the rest of space, just along the curve. Then first of all, we differentiate the components with respect to distance along the curve, right? ds, where s just represents distance along the curve, measured in whatever units we like. Right? But this in itself is not a true vector. Right? The v's may vary for reasons having nothing to do with an actual physical variation of the vector, but having to do with variation of the coordinates as you move along. What do you have to do to make a vector out of it? You have to make the covariant derivative, which involves the gammas. Gamma nu. Oh, I'm using now the notation of relativity, nus and mus instead of m's and n's. It doesn't matter. We could, somewheres I jumped into space-time. Let's do space instead of space-time. mn, and s, let's say, no, p, let's call it p, and then there is a v, n, dx, p by ds. dxp by ds, that's a vector. Remember what this vector is? What is the name of this vector? dx by ds. That's the tangent vector. That's the tangent vector along the curve. And we worked out last time that this is the covariant derivative of a vector along a curve. Along a curve, it's the covariant derivative, where this is the tangent vector, and this is the derivative of the vector along the curve. Now, I'll just remind you, we defined the geodesic last time by saying this curve is a geodesic if the covariant derivative of the tangent vector is 0. All right? So let's just put that down. Let's write that down. The condition for a geodesic. V now is going to be replaced by dxm by ds. In other words, we're going to replace v by the tangent vector itself, and then the derivative of the tangent vector with respect to s becomes a second derivative, d second xm by ds squared plus gamma mnp. Now the tangent vector, now v is the tangent vector, so that's dxn by ds, and then dxp by ds. If the covariant derivative of the tangent vector is equal to 0, if, I'm not saying it's always true for any curve, but if the curve is chosen so that the covariant derivative of the tangent vector is 0, then the curve is a geodesic. In a sense, it's the straightest possible kind of curve that you can have in the space. If it's flat space, then the geodesics are just straight lines. If the space is a sphere, then the geodesics are great circles. In general, they're nothing of the sort. They're curves that go through the space, but they're the straightest possible curves. They're the curves that you would get by just focusing and going incrementally straight ahead. Okay, but now let's define something else. Let's define parallel transport of a vector. Supposing we have some vector which is not the tangent vector now. Let's come back to a general vector like this. This vector may not be the tangent vector. Here it is. It's v. And it's allowed to vary along the curve. Well, if this covariant derivative is equal to 0, then we say that that vector has been transported parallel to itself along the curve. In other words, this is as close as you can get to saying the vector is constant along the curve if its covariant derivative along the curve is equal to 0. One says that this vector has been parallelly transported along the curve. Okay? Can we always do that? Can we always take a vector at this end and parallel transport it? In other words, can we take a vector at this end and now move it along here in such a way that it remains, in this sense, parallel to itself? Yeah, we can. Let's just rewrite this slightly differently. Let's just write this. The small change in Vm as we move from one point to another, let's get rid of the ds, just multiply through on both sides. The small change in Vm is minus gamma mnp Vn dxp. So if I have a small incremental distance dxp here, oh, sorry, this should be a minus sign, right? Not equal to 0. Yeah, let's dvm, all I've done is solve this equation here, multiply through by ds, that's not important, and this tells me how I should vary the components of Vm as I move along the curve so that the covariant derivative is 0. In other words, this tells me how to move from one point to another. It tells me how to change V, the components of V, given the components of V at a starting point, and the Christoffel symbols, and the little differential displacement dx. It tells me how to change V to the next point. In fact, it tells me once I've updated it from here to here, I can do it again and again and again. And so it's always possible to choose the components of v along the curve so that the covariant derivative is equal to 0. All you have to do is to solve for how Vm changes as you move along the curve. By knowing it at any one point, you can find out how it moves to the next point, and so forth. So that's not hard. That's the construction and the definition of parallelly transporting a vector along a curve. To move it from one place to another, you just change v by an amount that's proportional to v, and that's proportional to the amount that you're displacing it, and is proportional to the Christoffel symbols. Parallel to itself. Parallel to itself. In other words, you have some curve in space. I have a vector, and I want to move it along the curve in space so that it always stays parallel to itself. That's what we're trying to do. Okay?
Just a little aside. I always like the Hot Wheel car example. If you have a globe and you move a Hot Wheels car along it so that the direction never changes, you get the great circle. Or even on an inner tube, the Hot Wheels car is the thing that always has the same direction, and it will give you the shortest distance.
That'll give you geodesics.
Yeah, right.
Right. But now we're taking a curve which is not a geodesic. First of all, a geodesic is a vector which has been moved parallel to itself.
So I was just used that as an example as keeping the same direction is the same as minimizing distance.
That's for a geodesic, yeah. But you can also parallel transport something which is not a geodesic. For example, you can transport a vector which is not the tangent vector. I want to transport this vector along that line. Now, if I take that vector and transport it along that line, then the tangent vector is the thing that I'm transporting. If the derivative of the tangent vector is 0, it's a straight line. But I can also take any vector, which is not necessarily a tangent vector, and start transporting it along the curve, whether or not the curve is a geodesic. Take any curve, take a vector, and transport it so that it stays parallel to itself. That you can always do. Parallel to itself and of the same magnitude.
Now, would this be the same as saying that the angle between the vector and the tangent vector is always constant?
No, that's definitely not what it says. Why? Because the tangent vector is itself changing. Let's do it a little differently here. Let's take a circle, and let's take a vector. There's a vector. Now I'm going to transport it along itself. I'm going to transport it parallel to itself. I'm having trouble keeping it exactly parallel, but notice by the time it gets down to here, it's become the tangent vector. Keeping it parallel to itself along the circle will make it the tangent vector over here. Over here, it's perpendicular to the tangent vector, and up here, it's the tangent vector again. Right? So if I take a circle in flat space, a flat space circle, and transport a vector parallel to itself, the angle relative to the curve changes. It's the angle relative to the neighbor which hasn't changed. The neighbor to this point, or to the vector over here, is this point over here. It's relative to the neighboring value that it hasn't changed. So we're moving it along incrementally along the curve, crazy directions, but always keeping it parallel to its neighboring value. That's called parallel transport. Yeah?
ds is any parameter. It's not the
ds could be any parameter along the curve. Right. It's canceled out of this equation here. Right. Right. So there's a notion of parallel transport along a curve. Okay. But now you could ask an interesting question. Supposing, does everybody understand what it means? It means as you move along the curve, even if the curve is turning, you make sure that the vector stays parallel to itself. Let me give you an example how you could do that. Physically in the real world, a gyroscope. You take a gyroscope. A gyroscope is a spinning object. Right? If you don't really forcibly change its direction and you just hold it by its tip or whatever it is, and you move it around, it will always face in the same direction. You don't have to move it along a straight line. You can move it along a curve. That gyroscope will transport parallel to itself. So a gyroscope is a physical implementation of parallel transport in space along a curve. Okay? You move it around, pay no attention to it, just move the tip of it, and because of its angular momentum, it will continue to point in the same direction, even if you transport it along the wildest, wiggliest curve. Right? That's the idea of parallel transport. So this would be the equation then that would govern, in 3 dimensions, for example, would govern the components of the axis of a gyroscope as you move it around.
Now, that's not the same as Cartesian coordinates relative to that point, though.
We haven't even introduced any coordinates. We have introduced
there's
coordinates.
perpendicularity implied here.
What's that?
There's perpendicularity implied with parallelism.
Perpendicular to what?
Well, in order to be parallel, it must be perpendicular to something that's perpendicular to it, right?
Yes. So let me say it a different way. Take 2 distinct vectors which happen to be perpendicular to each other, and now parallel transport both of them. They will stay perpendicular. Okay. 3 vectors forming a triad, which you could make by 3 perpendicular gyroscopes and transport them around, and they'll stay perpendicular to each other. So parallel transport sort of preserves the angles between vectors and so forth, and it's the closest thing that you can have to the notion of moving a vector around so that its direction and its magnitude stay fixed. Okay? That's the notion of parallel transport. In fact, it's possible to prove that the magnitude of the vector stays fixed, but mostly I'm interested in the direction now. But now we come to a funny question. How do I know that if I parallel transport a vector from one place to another along curve A, let's call that curve A, I started over here, and I transport that gyroscope over here till I get to here. How do I know that if I did it along a different curve, I would come to the same final conclusion? How do I know that if I transported it along a different curve, it wouldn't come out in some other direction? No, that equation is just a definition of parallel transport, and it refers to a curve. How do I know if I chose another curve, that in fact I would get the same result?
Well, I'm just saying you already canceled ds, so it doesn't refer to a curve.
It does refer to a curve. The dx's here refer to the curve. The s is only the parameter along the curve. The dx's are the sequence of little differentials along the curve.
Okay.
Right. So this definition of parallel transport, and in particular the idea of transporting it all along a curve, we could ask, does it guarantee that the result of a parallel transport leads to a unique final answer independent of the curve connecting the 2 points? Well, the answer is no, it does not guarantee that. And in fact, in general, it's not true. If you could say the same thing another way. Instead of parallelly transporting it along 2 different curves, let's imagine parallelly transporting a vector around a closed curve. That's an even better situation. Take the gyroscope and parallelly transport it around a closed curve. Does it necessarily come back to the same direction? Okay? The answer is, in flat space, yes, that's intuitively obvious.
Right, but the bending of light rays around the star.
Well, right. But the question is, in a general space, in a curved space, is it necessarily true that if incrementally, from point to point, you make sure that you keep the vector parallel to itself, the gyroscope, must the gyroscope come back to itself? And the answer is no. The obstruction, or the fact, or the condition, the situation in which it doesn't come back to itself is the situation in which there is curvature. That's the diagnostic test to find out if a space is flat or not, is to transport vectors around curves. And if you ever find a curve that you can take the vector around where the vector does not come back to itself, somewheres in there is some curvature. That's the definition of curvature. That parallel transport around a closed curve does not bring you back to the same vector. If there is curvature, it's quite obvious that you cannot flatten the space out to give it a metric which looks like a conventional flat space metric. Yeah.
Does a Mobius strip have this property?
Sort of, yeah. Let's see. A Mobius strip, actually, when you go around a circle, a vector can flip its flipper. Yeah. But yes, a Mobius strip does have a kind of global, I'll call it global curvature, and I'll come back to the Mobius strip in a minute. Mobius strip is a non-orientable surface, and so it's a little bit peculiar, but we can certainly find examples without going to non-orientable surfaces. The cone is the sort of simplest example of all. The cone is a space which is, by the cone, everybody know what I mean by a cone? Like an ice cream cone? It's what you get if you take a sheet of paper, cut out an angular wedge. All right, there's an angular wedge. I wish I had a knife. Does anybody have a scissor with them? Yeah, I know I can do a trick, but let me. What do I do with the cover to this? Ah, okay. Ah, my knees. Oh, cool. Okay. Okay, so let's cut out the angular wedge. It's called an angular deficit or an angle deficit. I should have brought a big piece of, what do we call that kind of paper in kindergarten? Oak tag, yeah. A big piece of it and cut it out. So you cut out a wedge like that, and then you sew it together along the wedge like that, and you make a cone. Is that obviously a cone? Yeah, that's obviously a cone, right? Now, once you sew it together that way, you could cut it and slice it some other place and open it up. So it doesn't matter where you cut it and open it up, but wherever you cut it and open it up, it looks like that. Now notice, it looks pretty darn flat, but when you put it together like this, it no longer looks flat. And in fact, you can't flatten it out, not without smushing it and stretching it. So the cone is a curved space. But it's a curved space of a very special type where there's no curvature anywhere except at the tip. Let's see if we can refine that and understand it. So let's start with a cone. I'll first draw it as a cone. Here's the tip up here. And of course, a real mathematical cone goes on and on forever. It doesn't terminate at this point over here, but we can terminate it because I can't draw it forever. And then we come with our scissors. I don't think I need this anymore, but let's leave it here. I might want to do some more. we cut it, open it up, and it looks like, I guess, like what's that? Yeah, a pie with a slice taken out. All right, so that's a cone with a rule. The rule is that point over here is identified with a point over here. For example, if a fly walks around across here and crosses the red line, then in this map over here, think of this as a map of the cone, the fly walks around over here and then jumps over to here. The red line has been sliced open, but then we have to remember to identify points in the appropriate way. That's the mathematical construction of a cone in terms of a flat space. Now, notice that this sheet of paper, as well as this drawing over here, is completely flat everywhere along here, as long as we keep away from the problematic areas where we've cut it and the tip of the cone over here, it's completely flat. So first of all, let's take a closed curve over here. That's a closed curve on this flat sheet of paper. And now take our gyroscope and transport it around. We're taking the gyroscope and transporting it around the closed curve, parallel to itself at every point. All right, so whoever's doing this parallel transporting, as he moves it, he makes sure that incrementally it stays in the same direction. And as he goes all the ways around, guess what? What happens to it? It comes back to itself. All right, so there's an example of a parallel transport around the closed curve where the vector did come back to its original value. But now let's parallel transport around the tip of the cone. All right, so now we're going to take a curve that circumnavigates the tip of the cone. All right, and in particular, let's start with a vector. Just for the sake of clarity, I think I find it a little clearer. Let's start with the vector being aligned along the red line. And let's parallel transport along the curve. All right, first of all, the curve on here looks like that. It's a circle. It's a piece of a circle when we open it up. And the vector starts out in this direction. Whoops. Starts out by assumption along the red line. Now we move it parallel to itself. Parallel to itself does not mean that we move it so that it's pointing radially out. That's not parallel to itself. Parallel to itself means we keep its direction fixed. And by the time we get over to here, it's now pointing, in this case, practically perpendicular to the red line. What's going to happen, supposing we now close this up, we might slice it along some new place, we might slice it along a new place and close it up over here so that we close it up back into the curve over here. Look what it's done. It's gone from something which is parallel to the red line to something no longer parallel to the red line, and that means when we parallelly transport it around, it's going to come back to some new vector, which is going to be perpendicular, or not perpendicular, but at some angle relative to the original vector. In other words, it's quite clear. When I close this up, this vector will wind up coming out in this direction. Just think about closing this up, and this vector over here will wind up pointing in some new direction. So here's an example of parallelly transporting a vector at every stage, keeping it parallel to itself, and by the time it goes around a closed curve, it's not parallel to the starting point. Right? Only, notice that only happens if we go around the tip. If we steer clear of the tip, that doesn't happen. Okay. The tip is the point at which there is curvature. All right, so the tip, the diagnostic test has, I don't know whether we should say it failed or it succeeded. It's failed to demonstrate that the space is flat. It has succeeded in finding a point of curvature. Why do I say a point of curvature? Because if I circumnavigate any other point, I find no shift in the direction, but every circumnavigation of this point gives me the same angular shift. So what does it do? The presence of this point of curvature has the effect of rotating vectors which have been parallel transported around in a closed curve. It doesn't matter that this closed curve is a circle. It could be any closed curve around the tip. It will always rotate the vector by the same angle. Incidentally, if we started with a vector which was not along the red axis, but some other direction, and we went around, again, it would still come out in some new direction. And how about this angle, the angle that the vector gets rotated? How much is that? That depends on this angle here. This is called the angular deficit here. It's the amount that was bit out of the pie. Let's call it theta. When you take a vector around this closed path, it gets rotated by the same angle theta. So one might say that there's an amount of curvature which is parametrized by the angle theta. The bigger theta is, if theta is a very small angle, in other words, if it's just a very, very tiny piece of pie were taken out, then there's very, very little change in the direction of the vector that's been parallel transported. The bigger that the angle theta is, the more rotation there is in this vector. So that's an example of a point of curvature. Now let me point something out, that here we are, we're going to parallel transport around this particular curve. Nothing can depend on whether the tip of this cone here was truly pointed or whether I came along with my sandpapering machine and whittled off and made it smooth. Okay. So somehow the effect of going around this curve is the same whether this has been smoothed or not. However, supposing I go around the curve very close to the top here, then I'll get a different answer than on the cone. Then I'll get a different answer. In fact, I'll get a much smaller angle at the top of the cone here than if I go around here. Okay, so somehow this operation of going around this particular curve has located the fact that there's some curvature in there, but it hasn't told me the details. This particular curve has not diagnosed whether there was a point of curvature here or whether there was a smooth curvature there, but it's told me there is some curvature in there because when I go around the curve, because when I go around the closed curve, I don't come back to itself. So let's see now. Oh, let's do a sphere. Let's do a sphere. A sphere is also curved.
Question?
Yeah.
When you say parallelly transported, can you nail that down a bit more?
No.
Because if that's the angle to the circle going around, then that basically defeats the argument. And
Sorry?
It's not radially out. I can understand why it's not radially out. If it's pointing towards at infinity, then again the argument.
We take the curve and we break it up into lots of little straight lines, okay? And then we parallel transport from one to the other. And I'm not sure how to say this right. We're not transporting the vector so that it stays at the same angle to the curve. We're transporting it so that it stays the same angle to itself.
But if it's a geodesic, does it stay at the same angle to the tangent?
Right.
I have a question.
So that I think that helps answer that question, because in a sense parallel transport, if that's
Right.
constant direction, then parallel transport is constant with respect to the constant
That's
direction.
right. If you parallel transport something along a geodesic, it will stay at the same angle to the geodesic. At least in 2 dimensions. 3 dimensions gets a little more complicated because a vector can twist around. So there's something called torsion where the vector can twist around. But at least in 2 dimensions, that if you transport a vector on a geodesic, then it will stay at the same angle to the curve.
But on a cone, that would be sort of a spiral.
Say it again?
On a cone, a geodesic would look like a spiral. It wouldn't be just a circle cut perpendicular to the axis.
The geodesics on a cone are simply the geodesics that it inherits from flat space. So straight lines in here are geodesics on the cone. Yeah.
Well, they will, they'll get curved when you curl them up, right?
Let's say it again.
They'll get curved when you curl them up?
Well, when you see the straight lines on here, they're geodesics. Also, the straight line here is a geodesic. The straight line here is a geodesic. I don't know, would you say they get curved when you, yeah, sort of. If you're looking at it from the top, they appear to get curved.
The point is, what happens when a straight line crosses the identified,
When the straight line crosses where?
the lines that were identified? It no longer looks straight unless it actually has
Okay.
an angle.
Right, right. What you do, if you're interested in a geodesic which crosses here, then what you do, that's like a geodesic which crosses from here to here. Then the thing to do is to close it up over here, and this is going to be hard. And I don't want it to fall apart. And open it up over there. Okay? It's the same space, and now the geodesic that goes across the original thing can be drawn. All right? And you're right, what will happen is that when I open it up again, that geodesic which went across here will look bent. The geodesic which crosses across here will look bent, but when I close it up again, it'll look straight. Okay, so there is a geodesic, for example, which connects this point to this point. It doesn't go around here. It goes across here and then changes angle and goes over here.
And that angle would be repeated on the slice you made on the other side to make it parallel.
Yeah, for example, if the angle was 90 degrees over here, then it'll be 90 degrees over here.
What I was saying is once you close that up,
Yeah.
by making the other slit,
Oh, yes.
the angle becomes the same as
Yeah.
the other.
Absolutely. Absolutely. But this curve from here to here will then become a smooth straight line. Right. So if you're interested in curves that go from here to here, the thing to do is not to use this representation, but close it up over here and open it up somewhere else. And you can always do that. So cutting and pasting is the way to think about cones. So we do see that there are situations where parallel transport along a closed curve does not bring you back to the same thing. And when you don't come back to the same thing under such circumstances, that is the diagnosis of curvature somewhere in the geometry. Usually, and typically it means that there's curvature somewhere inside that curve, somewhere in the interior of that curve. Curvature in higher dimensions is a little more complicated. We'll come to it. But let's just do a sphere for a moment. Let's take a hemisphere. I'm interested in the sphere, but I just want to draw a hemisphere for the moment. And now I want to parallel transport a vector around not a great circle, but some other circle. A great circle is a geodesic. A great circle, the great circle being, for example, the equator. So parallelly transporting a vector along a great circle just means keeping the angle relative to the great circle fixed. But that's not true of a curve which is not a great circle. Parallel transporting is a little more complicated, and here's a simple way to think about it. Think about the bug moving along here, carrying his little gyroscope with him. Can that bug, who can only see an infinitesimal little distance around him, can he or she tell that this curve was not a curve, on a cone? A cone which has been fit so that it's tangent to the sphere. Can everybody visualize that cone?
Yeah, I don't think you can. You just said so.
Right. It's a dunce cap. It's a dunce cap on a spherical head. And it just happens to be tangent right along that curve. What's going to happen when I transport parallelly a vector around there? It's going to do exactly the same thing as it would have done on the corresponding cone. Okay? How big is the angle deficit of the cone? Well, that depends on where I draw this curve. For example, if I draw the curve up here, the angle deficit, there'll be less of an angle deficit. It'll be a flatter cone. It'll be more like this. In fact, if I make the circle a very small one, way, way up close to the North Pole, then that cone is practically a flat cone with a very, very small angular deficit. So the answer is, if I take a vector around the North Pole, staying very close to the North Pole, transported around, the angle may deviate a tiny bit, but not very much. If I take it around at 45 degrees here, you'll discover a fairly large angular deficit. And so, but in any case, the point is that the sphere is curved. We've diagnosed the sphere by transporting vectors parallelly to themselves along closed curves and found out that they don't come back to themselves. Not surprisingly, that means that there's curvature on the sphere, that the sphere is a curved surface. It also means that you cannot find flat coordinates, delta mu nu type coordinates on the flat sphere. So curvature is the obstruction to flattening a geometry out and making it everywhere flat. I'll tell you the fact now that if you have a curved geometry and you go around a small curve, then of course the angle deficit is small. Okay? So if you take, in any geometry, as long as you take a small enough curve and you take a vector and parallelly transport it around, the deviation of the direction will turn out to be small. You can see that on the sphere here, that up near the North Pole of the sphere, the corresponding cone has a very small angular deficit. How much of an angle, how much of a rotation do you think occurs for a given circle up here? Is the angle here proportional to the distance or what? Anybody know? The area. The area, right. This is something that's worth working out. You can work this out by yourself. It's just a question of taking a small circle up here, fitting it to a cone, All that means is here's your circle. Here you have your 2 points that correspond to the circle, and draw the tangent vectors. How much of an angle is involved? The angle will be proportional to the area of that little region. So it's the area that controls how much of a deficit or how much of a displacement you get when you go around a small circle or a small curve. Yeah.
Even if the area is not circular.
Even if it's not a circle, the displacement and angle will be proportional to the area. All right, so we can write down, let's call it delta theta. Well, let's just call it delta theta, the angle that the vector fails to reproduce the original direction. That delta theta will be proportional to the area of the enclosed curve times something, a number. And that number is called the curvature, R. For example, if I have a very big sphere and I take the same little area over here, I'll get a very small angular deficit. On the other hand, if I take a small sphere and take the same size circle over here, I'll get a rather large angular deficit. The smaller the geometry, the bigger the curvature. The smaller the geometry, the bigger the curvature. That's the curvature of a two-dimensional surface, is the relationship between the area of small little curves and the angular, let's just call it the angle deficit that's suffered when you go around the curve. Yeah.
The area here, the area on the surface, or the area of the projected surface?
Well, it really doesn't matter because we're talking about, we should be talking only about very small areas. So let's call this delta area. In other words, the right thing to say is that for an infinitesimal area, you get an infinitesimal angle, and the coefficient is called the curvature. And it doesn't matter in detail what the shape of the curve is. That's something you need to prove, but it's a true statement. Yeah.
In case of the conical example,
Yeah.
vectors that we're talking about must lie on the surface of the cone. It's a two-dimensional space, correct?
Yeah.
In the case of the three-dimensional sphere, is that also true?
No, the surface of the sphere is two-dimensional.
The vectors, however, do not lie on the surface of the sphere. Do not have to lie on the surface of the sphere.
You can think, that is a good question. You don't usually think of vectors as lying in the space. You usually just think of the vectors as having a magnitude and having a direction. So you can think of the vectors as sort of lying in the tangent space to the surface. The vectors, you don't think of the vectors as being creatures which live on the surface. They're creatures which have a direction and a magnitude, and they point along the surface, but they don't stick to the surface when the surface changes. So you think of them as things which live in the tangent space. Okay, that's the official words. But yes, you're right. I mean, the vectors don't really literally exist in the space itself. They're mathematical objects which live in the tangent space.
If you go around the equator and have
Yeah.
a tangent vector, that's going to work just fine, and yet there's an area deficit there, isn't there?
Yeah, but this formula is only for small areas. For large areas, you have to work it out in general. There's some integral to do, and that's right. Now, somebody asked me about the Möbius strip. The Möbius strip is a funny thing. How do you define a Möbius strip? You define a Möbius strip by taking a strip like that and then making identifications that this point over here is equivalent to this point, A. This point over here is equivalent to this point, BB. The vector from, or the segment from A to B is equivalent to the segment over here from A to B. But quite clearly that means if you take a vector around the Möbius strip, it changes, it flips its direction. So that's an example of a kind of curvature. But Möbius strips are so weird that they don't fall into the same classification. They're non-orientable surfaces, and they get you confused.
What is it you're calling it? That's, in my language, it's called a Möbius band.
Okay.
And you're calling it what?
Möbius strip.
Not just neither.
It's MO umlaut.
Möbius.
Oh, okay. Okay, it's pronunciation. Same word, different pronunciation.
Möbius.
Forgive me for being American.
Excuse me.
Well, it's Möbius in the same sense that amoeba is.
Is it? I don't know.
No, it's
I believe you.
M-O-E-B-A, right? Amoeba.
Wait a second. When Möbius was a person.
No, I'm just saying that it's anglicized to pronounce
Oh,
the way
okay.
we do.
Right. That's right.
Raises a question about the torus.
The torus, good.
Yeah,
All right.
because that's
Yeah.
also a rectangle with identifications.
Right. So the mathematically idealized torus, which is made in the way you just said, is flat. It is strictly flat when the torus is defined in the way that you said, which is a rectangle with identifications across the rectangle. A real torus, like the bagel, the surface of a bagel, is curved. But it has an integrated curvature, which is 0. We'll come to that. Well, maybe we'll come to it. The problem is you can't construct a flat torus in 3-dimensional space. You can do it in 4-dimensional space. You can't embed it in 3-dimensional space. Actually, you can. I just realized you can.
Not so. It's intrinsically flat, but you can't get a flat embedding.
Yeah, I'm going to make a flat embedding for you. All right, here's the rectangle. What we want to do is identify this edge with this edge and this edge with this edge. Some people don't know what I'm talking about, so I'll explain it. A torus is the surface of a bagel or a donut, and it looks like that. Just think of the surface. We're not thinking about the interior, not the good stuff that you eat, but just the surface. And now cut it. Cut it open over here and open it up. What does it become? It becomes a piece of a cylinder, right? I mean, just topologically, it has the properties of a piece of a cylinder. And now, when you've done that, cut it along here. Cut it along here and open it up. And what does it become? It becomes a rectangle. It becomes a rectangle. This edge over here is identified with this edge. So that means this edge over here, A, B, C, D, becomes A, B, C, D. A fly which walks across from here to here, walks across here and reappears over here. And the bottom, A, B, C, is identified with the top A, B, C. Okay, that's a torus. And clearly that torus can be drawn on the blackboard so that it is flat. Normally, when you draw a torus, it's curved. Over here at this edge here, it almost looks like a sphere, so it must be curved over here. In the inside over here, it has negative curvature. On the outside, it has positive curvature. So far, we haven't defined the sign of the curvature. But, question, can you take this sheet of paper and fold it together so that it forms a torus? Well, yeah, you actually can. You fold it together. You got to put a fold in it. All right. Now, this edge has been identified with this edge. I could take a piece of tape and fold it. Now I want to identify this edge with this edge. So I fold it again, like that. I don't even need to fold it. I just do this. And now think of a bug walking around. The bug walks around from here, comes out on this side, comes around over here, comes out on this side. So that's going around the torus this way. Or can go around this way. That's going around the torus this way. So in fact, I can make a flat torus. It's just a little bit, not much nourishment in it. Well, actually, there is no integrated curvature on the edge. No. It's got a little bit of positive curvature on one side, a little bit of negative curvature on the other side. Yeah. So it's a little bit degenerate, as you say. And but in 4 dimensions, you can draw a surface, a 2-dimensional surface that is an absolutely flat torus. So a torus can be flattened. A sphere cannot be flattened. Interesting difference. And yeah. Now, notice what we're doing. Yeah.
But the constant, I mean, if you draw small circles at various places on the torus, do you get angular deficit and surplus as you go around?
Are you asking me about positive and negative curvature?
I'm asking you if delta theta equals r delta A, what this,
You're asking me about
what values do you get for r? You don't always get 0.
on a flat plane, 0.
No, but on the torus.
Oh, no, that's on a real torus, meaning one which is embedded in 3 dimensions. There's curvature all over it. Different values, and in particular, on the outside of the torus. I'm going to explain now the sign of the curvature, and then we'll come back to, and I'll tell you about the torus. Okay. There's a notion of the sign of the curvature, and here's the way it works. Look down from the top, and let's go around clockwise or counterclockwise, either way. Let's see. We're going to go around this cone, around the cone. Oh, incidentally, in the case of the cone, what is the curvature? How much curvature? What is the numerical value of the curvature? The numerical value of the curvature is 0 everywhere except at the tip, and the curvature at the tip is?
The angle deficit.
No, it's infinite. It's infinite because the curvature is the ratio of the angle deficit to the area, and I can take an infinitely small area and still find that angle deficit. So the curvature at the tip of the cone is actually infinite. It's an example of infinite curvature. Infinite curvature means a singularity in the geometry, a place where it's not smooth. Okay, so we have the idea of curvature, but now what about the sign of the curvature? So let's take a vector, let's say pointing perpendicular. Let's amuse ourselves by taking a perpendicular vector and parallelly transporting it around to here. By the time it gets over to here, it will be pointing in the same direction, be sort of pointing this way, parallel to itself, and now close up the angle. Close up the angle, and which way is it pointing after you close up the angle? It's pointing kind of this way, right? All right. We've transported the vector in the counterclockwise direction. We've transported it counterclockwise, and which way did it rotate? Same way. Rotated the same way. And so we could give signs to these things. We could say that that going around this circle in the counterclockwise direction, let's define that to be a positive little area. Let's imagine now that areas can have signs. Here's the way we assign a sign to an area. If we have a little area and we go around it counterclockwise, we call that area positive. If we go around it the other way, we call it negative. So areas are things which have a sign. You don't usually think of an area as having a sign. But think of the area as having a sign because it's not just an area, it's an area plus an oriented boundary. There's a sense, we're imagining a sense of direction around the boundary. For counterclockwise, let's call it positive. For clockwise, let's call it negative. Then, on the sphere here or on the cone, if we go around clockwise, delta theta is also clockwise, and that corresponds to positive curvature. Since delta theta and delta area have the same sign, in other words, if we go around the area clockwise, we transport around a curve which goes around clockwise, delta theta is also clockwise, that's positive curvature. Is there such a thing as negative curvature? And the answer is yes. It's not hard to manufacture geometries which have negative curvature. It's a little harder to see, not nearly as easy to see. But if you take a saddle shape, a mountain pass, is it clear what shape that is?
Pringles potato chip.
What's that?
Pringles potato chip.
Yeah, potato chip, right, exactly. That's right. A Pringle, is it Pringles?
Yeah, they're the ones that molded. They aren't truly...
They're bad.
They look like it.
No, let's take Kettle's potato chips or something. Some good one. Yeah, that's right. The potato chip or the saddle surface. The saddle surface has the property, believe it or not, that if you go around the closed curve, clockwise around the closed curve, the transported vector rotates in the opposite direction. All right? Here's the way you can think about negatively curved surfaces. In particular, we made a positive curvature singularity by cutting out a piece of the pie, right? I'm going to show you how to make a negative curve, and you go home and do this and prove to yourself that what happens is what I say happens. We're going to make a cut. And now instead of cutting out a wedge, we're going to add something, we're going to add an extra angular piece in. An angle excess instead of an angle deficit. Here's the way we do it. All right, here's our angle excess. Right here, I take my surface, I open it up, notice it gets kind of floppy, and stick the angle excess in, and now tape it along here and tape it along here, and I have now, instead of an angle, can everybody see it? Instead of an angle, a piece of angle missing, it has more than 360 degrees going, instead of having less than 360 degrees going around, it has more than 360 degrees going around. Doing that makes a piece of negative curvature. If you transport a vector around that, you'll find out that if you transport counterclockwise, the vector rotates clockwise. That's a surface of negative curvature. So negative curvature and positive curvature both exist. Negative curvature is a little bit less intuitive because it doesn't involve things like spheres, but rather things like, I don't know how to describe them. I'm not sure. Say it again? It is the inner surface of the torus, absolutely. That's what I was going to come to, right. It is the inner surface of the torus. So the outer surface of the torus, by the outer surface, I don't mean looking at the torus from the dough. I mean, the outer surface is the part around here. The inner surface of the torus is that part. The inner surface is more saddle-shaped. The outer surface is more sphere-shaped. You'll discover that the outer parts of the torus, in other words, the boundary out here, is positively curved. The portion in near the hole there is negatively curved. and the total integrated curvature. If I integrate the curvature, what does integrating the curvature do? Forget it, not important right now, but there's as much positive curvature as there is negative curvature on the torus. On the other hand, the sphere is everywhere as positively curved. Okay, so we now have the basic idea in 2 dimensions of what curvature means. And the most important thing for us is that curvature is an obstruction to flattening the geometry. Flattening the geometry, by definition, means finding coordinates where the metric is just delta mu nu. All of these words are exactly the same in space-time. They're exactly the same. There are curves in space-time. You can take closed curves in space-time. You can transport vectors by exactly the same rules. The rule being right here. The Christoffel symbols are constructed from the metric in exactly the same way. And the notion of curvature, space-time curvature, is the same as the notion of just spatial curvature. It is harder to visualize. It's much harder to visualize the geometry of space-time than it is of just ordinary space. We weren't equipped with the mental architecture to visualize space-time, but the rules are essentially the same. So a curved space-time is one, if you like, which when you go around closed paths trying to keep a 4-vector, a space-time vector parallel to itself, you won't be able to because there's curvature in the middle. We're going to define next time the curvature tensor, but the basic idea of general relativity is, first of all, that space-time is curved, and second of all, the curvature is due to masses, is due to mass, or more generally, energy and momentum. E equals mc squared, of course, is the equality or the equivalence between energy and mass. Energy and mass are the same thing, except for a conversion factor, the square root of the speed of light. Energy and momentum, we'll find out, come together, but energy and momentum are the things which create curvature. That's the analog of the statement that mass creates gravitational field, and gravitational field that cannot be removed by a coordinate transformation. Gravitational field that cannot be removed by going to an accelerated frame of reference. That's the presence of a chunk of mass. It's an obstruction to getting rid of the gravitational field. Energy and momentum create curvature. Curvature is also an obstruction to getting rid of the curvature of space-time. So that's the basic theme. We're going to write down, if not derive, the equations relating the curvature of space-time to the presence of energy and momentum. And then we're going to talk about how particles move in a curved space-time. And the answer is they move along geodesics. So what we're going to do, here's the goal. Start with some energy and momentum, some mass. Calculate the curvature around it. And then that gives us a set of geodesics. And what we're going to want to see is that those geodesics behave almost identically to the way Newtonian trajectories move around a mass in Newtonian gravity. Of course, we're going to do a little better than that. We're going to see that there are some corrections to Newton, but that's the goal. Curvature is like gravitational field. It's created by mass. Solutions of F equals ma are essentially just geodesics in space-time. That's the goal for the next couple of lectures, and then we'll try to study some particular examples, in particular the Schwarzschild geometry of a chunk of mass. And I think, I'm not sure where we'll go after that. Any questions? Absolutely none. And
I have a a space embedded in another space, you said. They said the upper space, the higher space is flat. Then is parallel transport sort of equivalent to keeping parallel in the upper, in the higher dimensional space?
Well, okay, so let's see. So, no. Parallel transport is not defined by staying parallel in the embedding space. Yeah. Let's put it this way. Take three-dimensional space and now make a curved surface in it. If the rule for parallel transport was to keep the vector parallel in the three-dimensional sense, then when you went around any curved, there would be no such thing as curvature.
No, but you keep it parallel for a little ways and then project it. And you keep it parallel and project it.
Okay, when you parallelly transport a vector in the two-dimensional space, you keep it in the two-dimensional space. It's always pointing in the two-dimensional space. Yeah, you can probably think of,
You can understand it better if you think that for it to be a vector, it has to be just two numbers. It cannot be three numbers.
That's right. That's right. But let me give you another way to think about it. As we said, we can always find coordinates at a point which are delta mn. All right, that means that the coordinate axes locally at that point are perpendicular to each other, and in fact, they're as straight as possible. Right? Parallel transport from one point to another point in the vicinity of this point where we've made the metric look like this is just keeping the components of the metric, the components of the vector fixed, transporting it as if space was flat. The problem is that when you go over to here, the original coordinates here, for which the metric was just delta mn, are no longer the coordinates at this point where the metric is delta mn. There's a little bit of shift of coordinates to keep them to the new coordinate system, and so, okay. It's a little more complicated. Anyway, familiarize yourself as much as you can with the idea of parallel transport. And the next time, we will define the curvature tensor. And again, the curvature tensor is always related to what happens to a vector when you parallelly transport it around a curve. It's more complicated in 3 dimensions. Why? Because the curve could be oriented along any plane. And furthermore, the rotation of the vector could be a rotation about any axis. In 4 dimensions, it's even more complicated, but the basic idea is go around a little curve oriented along some plane and see how the vector rotates in space or in space-time. And that rotation of the vector, when you go around a little circle, that is what defines curvature. That's the notion of Riemannian curvature. And it's the notion that that's at the heart of the gravitational field. Okay.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.
That's Marla, yeah. That's my wife.
Which woman are you pointing to? No.
Here.
Carol.
Oh, is that?
The person you just pointed to was
I
Jean
see.
Carroll.
Who is that? Who is this?
Point, your wife. And the woman on the right is your then wife,
I don't know.
Ivana?
This was the picture. I assume that's John Johnson. Is that?
That's Carol.
Carol? Because it's very blurry.